Bismillahirrahmanirrahim. I am Dr. Amir Badsha, lecturer in Department of Chemistry, Cohort, University of Science and Technology. Today the topic of our discussion is factor affecting nucleophilic substitution reaction, which include SN1 and SN2. And we will discuss in detail about internal nucleophilic substitution reaction. We will discuss what type of mechanism and what are the evidences and what are the factors which are favor internal nucleophilic substitution reaction. This is lecture number 12 from the course Organic Chemistry 2nd, having code Chem 322. The outline of our lecture will include introduction, then what are the factors which are affecting SN1 reaction and the factor which is affecting SN2 reaction, and then we will introduce to SNI reaction, it means internal nucleophilic substitution reaction, and the factor and the evidences of SNI reaction, and at the end we will mention some references from which we have taken this lecture and for you for further study if you want. There are various factors which affecting SN reaction. It means substitution, nucleophilic substitution reaction. Among them, the first one is the substrate. We know substrate is the molecule where substitution takes place. So this substitution take place both in SN1 as well as in SN2 reaction. But in SN1 reaction, we know that it involves the formation of carbocation, and we know about the carbocation that a tertiary carbocation is more stable than the secondary carbocation, and primary carbocation is more stable than the methyl carbocation. So it involves SN1 involves the formation of carbocation. So a reaction in which it involves the formation of tertiary carbocation will favor SN1 reaction. So the various substrates which are used for the creation of carbocation, they may include tertiary halides, or instead of halide other living group may be also used. Similarly, secondary halide, primary, and methyl halides. So in this case, the tertiary halide favor the formation of a carbocation which is more stable. It means tertiary carbocation. So the tertiary halide will favor SN1 reaction instead of SN2 reaction. In SN2 reaction, it involves attack from the backside. It doesn't involve the formation of carbocation. So for attack from backside, it is easy for a nucleophile to attack in the primary substrate or in the methyl halide substrate. Why? Because there is no hindrance from backside to be attacked, because here attack take place from the backside, not from the front side. If the backside is covered by the various substituent, then it will be not easy for a nucleophile to be attacked. So in case of primary halide and methyl halide, the backside a nucleophile can easily attack or easily reach to the backside. So for that, in that case, SN2 reaction will be favored. For example, in case of tertiary halide, the backside is blocked, so it will not favor SN2 reaction. Similarly, in secondary halide too, but in case of primary halide and methyl halide, the nucleophile can easily attack because here the backside is not attacked, blocked by the substituent. The substituent are less, so nucleophile can easily approach to them. So methyl halide and primary halide will favor SN2 reaction because here the backside is not blocked. The second important factor which affect nucleophilic substitution reaction is a nucleophile. Nucleophile mean the nucleus loving species. It means it is electron efficient and it is in search of electron deficient center. These nucleophile have plenty of electrons. These electrons may be in the form of negative charge or in the form of lone pair of electron. So on that base there are different type of nucleophiles. A nucleophile may be the strong nucleophile. The strong nucleophile is that one where there is negative charge on the species, is shown here on the alkoxy anion and imide anion. Here the negative charge is present, so these are, it is a nucleophile, but it can be a strong it is a strong nucleophile because this negative charge on oxygen or negative charge on nitrogen is not stabilized, so the density of electron is more. If the density of electron is more, so it will attack strongly on the electrophilic center, so such nucleophile will be the more stronger one. The second one is the moderate nucleophile. Such nucleophile has also negative charge, but the negative charge is stabilized. For example, in case of halogen, the negative charge is present. Here the electronegativity of halogen is more, so it can hold this electron, it cannot easily donate, so it can act as a nucleophile but moderately. Similarly, in case of tosylate, and this is the phenyl group, and along the phenyl group, this is the phenyl group, and along the phenyl group there is sulfonic group is present, negative charge, and here methyl group is present. This species can also act, here negative charge is present, and this species can also act as a nucleophile, but this negative charge is stabilized by resonance to this ring. Although it can act as a nucleophile, but the electron density is not so much higher, so it can act as a moderate. Similarly, in the carboxylate, the negative charge is present, but the negative charge is stabilized. Here negative charge present in oxygen, but it is not limited to this oxygen, it is stabilized over these both oxygen. So the new resonance structure can be written as C double oxygen will become single bond here, and negative charge will be appear, and here this bond will be converted into double bond. So sometimes the oxygen, the electron density is on this oxygen, and sometimes the electron density on this. So it's mean if the electron density is spread over the molecule, so it will reduce the electron density, and by decreasing the electron density its nucleophilicity will be decreases. Although still it acts as a nucleophile, but it can act only as a moderate nucleophile. The third one is the weak nucleophile. Here there is no negative charge, but has lone pair of electron. In this lone pair of electron may be present on the oxygen in case of water, or maybe in the alcohol, or may be present on the nitrogen, for example in case of ammonia, and for example in case of amide ion. Here the lone pair of electron are present, so it has plenty of electron density is more, but not so much high as like that of negative charge, so they can also act as a nucleophile in search of electrophilic center, but they can act as a weak nucleophile. So this is all about the nucleophile and about their nature. Now we are coming to the effect of nucleophile on SN1 and SN2 reaction. Now first we will discuss SN1 reaction. As we know that SN1 reaction takes place in two steps. In the first step, which is also called rate determination step, a carbocation is formed, and in the second step, nucleophile is attacked, which is a fast step. So nucleophile is not involved in the rate determination step, so that's why the nature of a nucleophile has no any effect on the SN1 reaction. Although if we use a weak nucleophile, so it will favor SN1 reaction, because if we use a strong nucleophile, so strong nucleophile will try to attack on the electrophilic center more. If we use weak one, so it will not attack, it will first allow to leave the living group, and then after that when a carbocation is formed, it will attack. So in that case, it is independent of a nucleophile. It has the nature of nucleophile. If we use strong nucleophile or moderate nucleophile or weak nucleophile, it will have no any effect on the SN1 reaction. But mostly for SN1 reaction, we use a weak nucleophile. The weak nucleophile may be in the form of water, or maybe in the form of alcohol or ammonia or primary amine. But in case of SN2 reaction, which is a concerted reaction which takes place in a single step, and that single step is the rate determination step. So both nucleophile as well as substrate involved in the rate determination step. So that's why the nature of nucleophile will affect the SN2 reaction. So definitely, if a nucleophile is a strong one, then it will favor SN2 reaction compared to a nucleophile which is a moderate, or compared to a nucleophile which is a weak one. So we can easily say that a nucleophile, which we use a strong one nucleophile, so it will favor SN2 reaction, and if a weak, then it will favor SN1 reaction. The third one is which affect the rate, which affect nucleophilic substitution reaction, is the leaving group. So leaving group leave, and then nucleophile attack. It depends upon on the type of reaction. In some case, the leaving of leaving group and attack of nucleophile take place simultaneously, for example in SN2 reaction. And in some cases, first the leaving group leave and then nucleophile attack, for example in SN1 reaction, in SN1 reaction, yes. But in SN2 reaction, the leaving of leaving group and attack of nucleophile group take place simultaneously. So the leaving group can affect both SN1 and SN2 reaction. Before to find the effect of leaving group on SN1 and SN2 reaction, we should know about the nature of leaving group, that what type of leaving group there are. So the leaving group are characterized into excellent, and then characterized into good, and the last one is the bad one. Excellent leaving group are those in which there is no negative charge, only has lone pair of electron. When a leaving group leave, after, for example this is X, and when it is leave, it has no charge is present on it. So after leaving, no charge is present, so it means it will be a stable one. So in that case, it is a good leaving group. For example, the example of good leaving group include water, because water has no any charge, or the second one is the alcohol, because it has also no charge, ammonia as well as primary amine. If these group act as a living group, so they will live as a living group, is a neutral living group, so they will be considered as excellent. A good leaving group is that one which has negative charge, because leaving group also a nucleophile. They will have lone pair of electron, or they will have negative charge. If it has negative charge and the negative charge is stabilized, for example in case of halide, for example in case of tosylate or carboxylate, they will be also considered is a living group. And what will be the nature? They will be the good living group here too, because here the negative charge is stabilized when after living. And the third one is the bad one. It has negative charge like that of the good one, but here the negative charge is not stabilized. For example, if alkoxy group leave is an alkoxy group, then the negative charge will be limited only to oxygen atom. Similarly, if amide group leave as such, then the negative charge will be limited to nitrogen. It will be not stabilized. So such species, when used as a living group, they will be not good living group. They will be considered as a bad living group. Now we have studied about the nature of living group in detail. Now we are coming at what will be the effect of nature of living group on the nucleophilic substitution reaction. Either it will be what will be the effect of it on the nature of SN1 and the nature of nucleophilic substitution reaction. In case of SN1, as we have mentioned earlier, that living group can affect both, the nature of living group can affect both SN1 and SN2 reaction. But in some cases it affects a reaction more comparatively. For example, as far as SN1 reaction, the living group should be excellent, at least excellent. A good living group can also cause SN1 reaction, but for SN1 reaction the most effective one is the excellent reaction. If you want to carry SN1 reaction during a nucleophilic substitution reaction, then the living group should be used the excellent one. If you do not use the excellent living group, then it is not possible for the reaction to be occurred. And for SN2, both SN2 reaction can be also affected by the nature of the living group. But for SN2, excellent is also good, but it can be also occur with a good living group. A living group should be at least good. If it is bad, then SN2, neither SN2 reaction will occur, neither SN1 reaction will occur. But if the living group is excellent or good, but mostly the excellent group favor SN1 reaction, and both excellent as well as good, but the good one is enough for the SN2 reaction. The fourth factor is the solvent effect. Nucleophilic substitution reaction involve the polar mechanism. So for polar mechanism, we should need a solvent which has polar in nature. But polar compound, but polar solvent is also further divided into two types. There may be protic solvent and there may be aprotic solvent. In the protic solvent, hydrogen is directly bonded to a more electronegative atom. For example, here in H2O you see in H2O, here hydrogen is bonded to a more electronegative atom, oxygen. Same is the case of in case of ROH, alcohol. Here hydrogen is also bonded to a more electronegative atom. And similarly in case of ammonia, hydrogen is also bonded to a more electronegative atom. So these are the polar, but these are protic polar solvent, because here hydrogen is bonded to a more electronegative atom. A second type of polar solvent are aprotic, where there is no hydrogen bonded to a more electronegative atom. For example, in case of DMSO, in DMSO, the structure of DMSO, where sulfur is bonded with oxygen, and on the other hand it will bond it to a 2-methyl group. So here you see there is no any hydrogen bonded to a more electronegative atom. This more electronegative atom is oxygen, and here is no hydrogen bonded to it. So it can act as a solvent. And what type of solvent? Polar solvent, but they are aprotic because there is no. Similarly, in case of DMF, and DMF, dimethylformamide, where carbon is bonded with oxygen and hydrogen, and on the other side it bonded to a nitrogen, and nitrogen is bonded with the 2-methyl group, and here is no hydrogen bonded with a more electronegative atom oxygen or more electronegative atom nitrogen. So it is considered a polar solvent but considered aprotic solvent. And similarly, in case of acetonitrile, it can also act as a polar solvent, but there is no hydrogen bonded with a more electronegative atom nitrogen, so they can act as a polar solvent, but they are considered as aprotic solvent. So these are about the solvent, about the polar solvent, the nature of the polar solvent. Now we are coming that what will be the nature of the effect of the nature of the solvent on the nucleophilic substitution reaction. Mostly the aprotic solvent favor the SN2 reaction. For example, this is a reaction which follow SN2 mechanism, because here the halide is the primary halide. So definitely in the primary halide, as we have discussed, the effect of substrate on the nucleophilic substitution reaction, primary halide favor SN2 reaction. Here the bromine is the leaving group and azide group, it is a nucleophile. So it substitute bromine is a nucleophile, and the position of this bromine is taken by the azide group. It follows SN2 mechanism. Now we study the effect of solvent on the rate of this chemical reaction. If we use methanol or water, which are protic solvent, where the hydrogen is bonded to more electronegative atom, here the rate is comparatively very slow. But if we change the protic solvent on the aprotic solvent, for example, if we add DMSO, then the rate is enhanced very sharply. Similarly, if the polarity of the aprotic solvent increases further, for example DMF and then acetonitrile, the rate of SN2 reaction increases enormously. So in the protic solvent, the rate of SN2 reaction is very slow, but in the aprotic solvent, the rate of SN2 reaction is very fast. Now the question arises here that how they affect, why it is so. You can see here that the aprotic solvent, we have discussed aprotic solvent favor SN2 reaction. Why it is so? The reason is that because when we use polar protic solvent, so it will stabilize the nucleophile. This chloride and it is a nucleophile, so it will stabilize it, and by stabilization of this nucleophile, its activation energy is increases. This is the activation energy of this substances. But when aprotic solvent is used, polar solvent, but it is aprotic, so it will not stabilize it. If it not stabilize it, so its energy will be high, If the energy is high, then the activation energy of that nucleophile will be less. If the activation energy is less, that then it can easily obtain the transition state. If it can obtain the transition state very easily, then the rate of that reaction will be high. But on the other hand, in case of SN1 reaction, the protic solvent power SN1. Why it is so? We know that during the protic solvent, the SN1 reaction, the carbocation is formed, and this carbocation is stabilized by the protic solvent. As you see here, if we use polar A protic solvent, here the carbocation which is formed is not stabilized more compared to the polar protic solvent. Here in protic solvent, this carbocation which is formed is stabilized. So when a stable species is formed, then that reaction will be proceed fast compared to that one where unstable carbocation is formed. So here in the polar protic solvent, the intermediate, it means the carbocation is stabilized, so this reaction will proceed fast compared to this one where the polar aprotic solvent has been used. So this is all about the factor which is affecting the SN reaction. I hope you will understand it now. The next one we will discuss the SNI reaction. So what is an I reaction and how it happened? SNI reaction, the example of SNI reaction has been shown here. Is appear from its name, it is substitution nucleophilic internal. It means substitution take place, but it is internal substitution reaction. For example, here you see that the OH of the substrate has been replaced by the chloride ion, where OH has been substituted by the chloride ion. But one thing should be noted here, that the in the substrate, the configuration of where the configuration was R, it still remain in the product. The configuration is still R. Such reaction take place in the presence of ether or THF, or no solvent is needed for such reaction. Now what type of mechanism is used? What mechanism, through which mechanism this reaction proceed? We know that OH, why OH? OH is not a good living group. We have discussed in detail in the previous lecture and in this lecture too, that the OH, when it is leave, so here negative charge is concentrated on oxygen. So here the density of an electron is more. If the density of electron is more, so it will be not a good living group, it will be a bad living group. Now how to convert this OH into a good living group? First we should convert them into a good living group. To convert them into a good living group, it should be protonated, and after protonation, then it can be easily detached or it can easily leave. So first, this oxygen which has a lone pair of electron attack on this sulfur. After attacking of the sulfur, these electrons will be shifted to oxygen. After shifting to oxygen, so negative charge will be appear on it, and by using this electron, positive charge will appear on it. Then this negative charge will come back and it will form a double bond with oxygen, and this chlorine will live as a living group. When this chlorine is lived as a living group, it will abstract hydrogen from oxygen and will form and will be changed into HCl and will be removed as and we will get this species. After getting this species, then this oxygen is in the form of OH, which was considered as a bad living group. Now it has been converted into a good living group, and it can be easily removed. How it can be converted into a good it has been converted, how it can be removed now. So this bond is shifted here, so it is converted into a double bond, and after conversion this bond into a double one, so this chlorine will leave in the, after leaving the chlorine will attack at this position, so we will get the substituted product where chlorine has attached to the same position from the same side where OH has been left, and along with this byproduct sulfur dioxide is formed in HCl, which has formed here in the previous step. So we get here, we have used R and still we have the product which has OR configuration. So how we will understand that a reaction has occurred through SNI mechanism? We know that from the previous lecture that in SN2 inversion of configuration, which is also called Walden inversion take place. But in case of SN1 reaction, we know that a racemization takes place. Half of the molecule is racemized and half of the molecule have the same configuration is like that of the reactant. But in SNI reaction, the stereochemistry will not change. For example, if we have started here from R and still we have R here, and how the configuration has been retained, we have discussed this in detail in this mechanism. What is the shape of intermediate which is formed during this reaction? Mostly it has been shown in books that a cyclic transition state is formed. A 4-center cyclic transition state is formed. Here is R is bonded with oxygen. Consider this is R group, and then it is bonded with the sulfur. At the same time, this bond is broke, and at the same time it is also bonded with oxygen. So sulfur is bonded with oxygen and R and R. So a 4-member cyclic transition state is formed in the SNI reaction. But mostly, as I have mentioned here, that in the solvent that we use, mostly it is a non-polar solvent and are no solvent. In the non-polar solvent are either RTHF. If we use solvent pyridine instead of THF or pyridine, the structure of pyridine is like this one. If we use pyridine as a solvent, then the reaction will not follow SNI mechanism, then the reaction will follow SN2. Why it is so? Let's consider this reaction. Here we have started from R and we have used cyanide chloride, and we use pyridine instead of THF or ether. Here the configuration is changed, and along with this, these byproducts are formed. Now if we consider the mechanism, then we will understand that how configuration has been changed. Here the chlorine ion are present in free form. In that case, the chlorine ion was not in plenty amount. Here the chlorine ion are free from in the pyridinium chloride form. How pyridinium chloride is formed? Look. Here in this case, again, if we consider the mechanism, these lone pair of electron attack on a sulfur, and this bond is shifted here, and after this we get this species, and then the negative charge restore and form a double bond, and this chlorine is left. This chlorine is taken by the ammonium ion. This chlorine is free now, and now both chloride ion are present and pyridine is present, but the capacity to take of hydrogen of the pyridinium of the nitrogen of pyridine is more compared to the chloride ion. So instead of chloride ion, this hydrogen is taken by the pyridine, and we will get a pyridinium ion. This is negative, positive charge will be appear on it, and it will form a pyridinium ion, and then this pyridinium ion react with the chloride ion and it form Pc, which is also called pyridinium chloride. When this pyridinium chloride, along with this pyridinium chloride, this species is also obtained. But here the chloride ion is much more compared to the previous reaction, so chloride ion can attack from the back side. By attacking from the back side, this group is leaving a sulfur dioxide, and chlorine is also removed. And by attack from back side, so we can get this species whose configuration is different from the starting material. The starting material has configuration R and it has configuration S. So in this case, the mechanism is not S in I. The mechanism is SN2, because here attack is taking place from the back side. Now, what are the evidences of SNI mechanism? First one is the kinetic mechanism, because it both affect by the concentration of the substrate as well as by the concentration of nucleophile. So the kinetics of the SN2 of the SNI reaction is a second order. It is a bimolecular reaction. Stereochemical studies, mostly the optical center retain. There is no change in the optical center. If we start from R, so in the product it will has also R configuration. If we start from S in the product, so the configuration of product will be also S, which means no inversion take place. The third one is the rearrangement. Mostly ion pair are formed, as we have discussed in the mechanism, in SNI mechanism, and if the ion pair are formed, if there is the stability by rearrangement take place, if there is a possibility, then it will occur definitely. For example, here this species is converted into positive cation species in anion species. Such species is also called ion pair, or it is also called Gajan pair. So this Gajan pair, it is the primary now. It is the primary carbocation, secondary carbocation now. So secondary can be converted into easily into tertiary when this hydrogen along with electron shifted here. Then the positive charge will be appear on this one. If the positive charge appear on this one, then the chloride will attack on this positive center. So which has been removed or left from here, and the chloride attack on this position. It means it doesn't attack on the position through which the leaving group has been left, but it attack on the other position. It is called sense substitution reaction that we will discuss in detail in the coming lecture. So why this? Because as rearrangement has been taken place. If the rearrangement occurs, if there is a possibility of rearrangement in the SNI mechanism, so definitely rearrangement will be also occur. These are the references for further studies. If you have any question about that, then you can contact me through WhatsApp, or you can email through the email which has mentioned in the bottom of each page. Thank you for watching this video.